The landing was perfect. That's the first thing you think as the vibration settles and the retro thrusters cut out and an alien world goes silent around you. 6 years of travel, 400 million miles of cold vacuum, and you stuck it. The lander sits level on the surface of Europa, Jupiter's fourth largest moon, and for exactly 4 seconds you feel the cleanest, most complete sense of accomplishment a human being can feel. Then the ice moves, not catastrophically, not like an earthquake, not with a sound. Sound doesn't carry the way you'd expect out here. It's a slow, grinding shift, somewhere beneath the landing struts, a tremor that travels up through the frame and into your boots, and your first instinct is that it's thermal settling, the vehicle's heat interacting with the surface. Routine. Expected. You've been briefed on this. But then it happens again. And this time, it's not beneath the lander. It's 40 meters to your left, where the ice plain stretches flat and pale toward a ridge of chaos terrain that looks like something enormous pressed up against the underside of the surface from below and then slowly, methodically, dragged its fingers across it. And this is when your training collides hard with the part of your brain that was shaped by a few 100,000 years of evolution on a planet where things that move without explanation generally want to eat you. You're on Europa. The ice is moving, and you're only beginning to understand what that means. Here's what no mission briefing fully prepares you for. Europa is alive. Not in the way that word usually gets deployed in science documentaries, as a comfortable metaphor for geological activity. Alive in the sense that it is in constant, dynamic, measurable motion. Its surface is being cracked and resurfaced and pulled apart and pressed back together by forces so powerful and so persistent that the entire moon is essentially a slow-motion mechanical system, grinding away at itself across timescales that dwarf recorded human history. And somewhere beneath the ice you're standing on, beneath the shell that might be 10 kilometers thick or might be only 3, depending on where you're unlucky enough to be standing, there is an ocean, a real liquid water ocean, larger than all of Earth's oceans combined, kept liquid not by the warmth of a distant sun, but by the gravitational violence Jupiter inflicts on this moon's interior every single time it completes an orbit. You're standing on a world-sized ice lid over the largest known body of liquid water in the solar system. And the lid is cracking. Stay with this, because it gets much worse before it gets better. And honestly, it doesn't entirely get better. Let's talk about what Europa actually is, because most people who've heard the name have a comfortable, sanitized version of it in their heads. A moon, covered in ice, possibly interesting. Candidate for extraterrestrial life. File it away. The reality is considerably more visceral. Europa is roughly the same size as Earth's moon, about 3,100 kilometers in diameter, and it orbits Jupiter at a distance of about 671,000 kilometers, completing one orbit every 3.5 Earth days. At that distance, Jupiter's gravity is immense, but Europa doesn't orbit alone. It shares Jupiter's gravitational neighborhood with Io and Ganymede, 2 other large moons, and the 3 of them are locked into what's called an orbital resonance. For every one orbit Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. They're synchronized, like a cosmic clock mechanism, and that synchronization has consequences. Because Jupiter's gravity is so powerful, and because Europa's orbit is very slightly elliptical rather than a perfect circle, the moon gets squeezed and stretched as it moves closer to and farther from Jupiter across each orbit. Not dramatically, the change in Europa's shape across a single orbit is only about 30 meters, but it happens continuously, relentlessly, on a schedule you could set your watch to. And all that squeezing and stretching generates heat. Not the kind of gentle heat you get from the sun on a warm afternoon. The kind of heat produced by friction, the internal friction of a rocky body being mechanically deformed over and over again, billions of times over the course of its existence. That heat keeps the interior of Europa liquid. Scientists estimate the ocean beneath the ice may be up to 100 kilometers deep. Compare that to Earth's oceans, which average about 3.7 kilometers deep. Europa's ocean, by volume, is estimated to contain roughly twice as much liquid water as exists on the entire surface of Earth. Oceans, lakes, rivers, glaciers, and groundwater combined. Twice as much. On a moon that most people couldn't pick out of a lineup. And this ocean doesn't just sit there, inert. The tidal forces that heat it also drive circulation. There's chemistry happening down there, energy input, the kinds of conditions that, on Earth, we now know are sufficient to support life without any input from sunlight at all. But you're not in the ocean, you're on the ice, and the ice is not what you hoped it would be. From a distance, from the Voyager probes that first photographed Europa in detail in 1979, or from the Galileo spacecraft that spent 8 years studying the Jovian system in the 1990s, Europa's surface looks almost pristine. It's one of the smoothest bodies in the solar system. It lacks the craters that pockmark almost every other solid surface we've studied, which is itself a clue. The surface is young. It's being constantly renewed, resurfaced by geological processes that erase the impact scars before they can accumulate. The current surface of Europa is estimated to be between 40 and 90 million years old, which in planetary terms is essentially fresh paint. What replaces the old surface is the chaos terrain. That's the actual scientific term, chaos terrain. Regions where the ice has been broken apart into rafts and blocks, rotated, refrozen, then fractured again in a different configuration. From orbit, these regions look like someone shattered a pane of frosted glass and then pressed the pieces back together slightly wrong, leaving dark lines and gaps and jumbled geometries where smooth plains should be. Up close, they're a landscape of angular ridges and tilted slabs, with surfaces stained brown and red by the organic compounds and sulfur compounds that migrate up from the ocean below through the ice, like minerals leaching through rock. The dark reddish-brown coloring isn't decorative, it's chemistry. It's evidence of a continuous exchange of material between the surface and whatever is happening below. The surface of Europa is not a sealed container. It breathes. But that's not the worst part. The worst part is the ridges. Europa's surface is covered in a network of double ridges, parallel raised features, some of them hundreds of meters tall and extending thousands of kilometers across the surface, that scientists now believe are formed when tidal flexing opens a crack in the ice. Liquid water or warm ice wells up from below and then refreezes as the crack closes. Then the crack opens again and closes again and refreezes again, over and over, building the ridge taller with each cycle, like a scar that keeps being torn open and healing wrong. Some of these ridge systems are geologically recent. Some may be forming right now. You are standing on a surface that is actively being torn apart and rebuilt by forces you can feel through your boots but cannot stop, cannot redirect, and cannot fully predict. Step outside the lander in your mind. Stand on the surface. The first thing that redefines everything is Jupiter. It hangs in the sky at roughly 24 times the apparent diameter of our full moon as seen from Earth. banded in orange and brown and cream, close enough that you can resolve the cloud structures with the naked eye, close enough that it doesn't feel like a backdrop. It feels like a ceiling that is, at this moment, pulling on every atom of the world beneath your feet. The surface temperature sits at around -160 degrees Celsius in the equatorial regions where you've landed. That's colder than the coldest temperature ever naturally recorded on Earth by about 100 degrees. Your suit is handling it. But the cold has a presence here that's different from anything in your training simulations because it's not just ambient, it's absolute. There is no atmosphere worth mentioning. Europa has a thin exosphere, technically a whisper-thin envelope of oxygen molecules generated when Jupiter's radiation splits water molecules in the ice. Its surface pressure is roughly 0.1 micropascals. For reference, a perfect laboratory vacuum is about 100 micropascals. The air here is 1,000 times thinner than the best vacuum we can create in a lab on Earth. The silence that implies is total. Jupiter's radiation environment adds another layer of threat that you cannot see, feel, or otherwise sense directly, but that your dosimeter is tracking with quiet, metronomic concern. Europa sits within Jupiter's magnetosphere, which accelerates charged particles to high energies and funnels them toward the Moon's surface. The radiation dose on Europa's surface is approximately 540 rem per day. A dose of 500 rem over 5 hours is lethal to an unprotected human being. Your suit shields you from the majority of it, but every minute you're on the surface is a minute of irreducible exposure, accumulating invisibly in your cells. And now, the ice shifts again. Not a tremor this time. A sound, conducted through your boots and up through your skeleton, bypassing the vacuum entirely. A low, resonant groan like a ship's hull under pressure. A ridge 50 meters to your north has moved, measurably. In the 10 minutes since you landed, the topography around you has changed. You need to understand what's below the surface, because that's where the real story lives. The ice shell of Europa is, depending on the region, somewhere between 3 and 30 kilometers thick. That uncertainty isn't a failure of science. It's a reflection of the fact that the shell isn't uniform. Some regions are thin enough that the ocean beneath is only a few kilometers down. Some are thicker, colder, more stable. The chaos terrain regions, those jumbled, refrozen rafts of ice, are believed to mark the locations where the shell is thinnest, where the ocean is closest to the surface, where the thermal and chemical exchange between the two is most active. You landed in the smooth plains. You chose your landing site specifically because it seemed stable. But the chaos terrain is not restricted to easily identifiable zones. It can develop, it can migrate. And if the shell beneath you is thin enough, if you are, by some navigational misfortune, parked above a region where warm water circulates close to the surface, then what you're experiencing isn't just routine tidal flexing. It's something considerably more significant. In 2013, the Hubble Space Telescope detected what appeared to be water vapor plumes erupting from Europa's south pole, columns of water shooting up from the surface into space, similar to the plumes observed on Saturn's moon, Enceladus. The detection was controversial, intermittent, and difficult to confirm. But in 2016, Hubble observed what appeared to be the same plume again, from the same location, at approximately the same scale. And subsequent analysis of data from the Galileo mission, collected in 1997, found evidence that the spacecraft may have actually flown through a plume without recognizing it at the time, because no one was looking for plumes yet. The ocean is not sealed. In at least some locations, At least some of the time, it finds ways to the surface, through cracks, through thinned ice, through the violence of tidal energy looking for release. And here is where things get terrifying, because you have just run the numbers again, and you realize the ridge to your north did not simply shift, it cracked. There is a new fracture in the ice plain, running roughly northwest to southeast, approximately 800 meters from your landing site, and it is slowly widening. The ocean of Europa has been the subject of increasingly serious scientific attention, not just because it exists, but because of what we think is happening inside it. On Earth, the discovery of hydrothermal vents on the deep ocean floor in 1977 changed biology permanently. Before that discovery, life was understood to be fundamentally solar-powered. Every food chain traced back ultimately to sunlight-driving photosynthesis. The hydrothermal vents destroyed that assumption. They host entire ecosystems, tube worms, crabs, shrimp, bacteria, living in complete darkness, at crushing pressures, in water that reaches temperatures of over 400 degrees Celsius, powered entirely by the chemical energy released when superheated water from the Earth's interior meets cold seawater. No sunlight, no photosynthesis, just chemistry and heat. Europa may have the same thing. The tidal heating that keeps the ocean liquid also likely drives geological activity at the sea floor, the same way it drives volcanic activity on Io, where the tidal forces are so extreme that Io is the most volcanically active body in the solar system. Europa is less dramatically heated, but the energy input is real, continuous, and substantial. If there are hydrothermal systems on Europa's seafloor, and there is no compelling reason to think there shouldn't be, then the ocean below you is not a cold, dark, sterile body of water. It is a chemically complex, energetically driven environment that has been in continuous operation for billions of years. Billions of years. Life appeared on Earth relatively quickly after the oceans formed, and the chemistry was right. The conditions that produced life on Earth took perhaps a few 100 million years to produce their first results. Europa's ocean has been liquid, warm, chemically active, energetically driven, for potentially 4 billion years. Whatever has had 4 billion years to develop in a warm, dark, chemically rich ocean the size of all of Earth's oceans combined is either nothing or something that we lack the imagination to fully anticipate. We haven't looked yet. No probe has ever pierced Europa's ice and descended into the ocean. Every instrument ever pointed at this world has observed it from the outside. What's down there remains, as of this moment, entirely unknown. Not theoretically unknown, actually, genuinely, completely unknown. The crack to your northwest is now 900 meters long and still propagating. In 1995, when the Galileo spacecraft began its extended survey of the Jovian system, scientists started mapping Europa's surface in detail for the first time. The network of ridges and lineae, the long, dark lines crisscrossing the surface, were catalogued, measured, and analyzed. And when researchers examined the oldest visible lineae and tried to reconstruct the geological history they implied, they found something that required a second look. The oldest lineae on Europa's surface appear to match a configuration that would be consistent with the surface having rotated, not the moon itself, but the ice shell, sliding around the interior ocean beneath it, a process called true polar wander, or non-synchronous rotation. The ice shell and the rocky core of Europa may be decoupled from each other, slipping independently, with the ocean between them acting as a lubricating layer. If that's correct, then the surface of Europa is not fixed to anything below it. It is a floating lid, drifting over an ocean, repositioning itself over geological time. But here's where the data introduces an anomaly that is less easily filed away. In studying the tidal flexing patterns of Europa's ice shell, researchers discovered that the shell deforms in ways that are broadly consistent with models, but with variations that are difficult to account for through simple tidal mechanics alone. The shell appears to be, in certain regions and at certain times, flexing more than it should. The energy input from Jupiter's gravity is well characterized. The output, the movement of the ice, occasionally exceeds predictions in ways that have been attributed variously to localized thinning of the shell, to convection within the ice itself, to thermal plumes rising from the ocean below. None of these explanations are implausible, but none of them have been confirmed with certainty either. And buried in the Galileo magnetometer data from the 1997 flyby, the same data set that may contain the ghost of a plume crossing, there is a brief, localized anomaly in Europa's induced magnetic field that has been noted in the literature and not yet fully explained. It lasts approximately 90 seconds. It appears in a region of the surface that was, at the time of the flyby, in the midst of active chaotic terrain formation. It was described, in the peer-reviewed paper that first addressed it, as inconsistent with a simple conductive ocean model and warranting further investigation. Further investigation has not yet happened, because no spacecraft capable of investigating it has yet been sent to Europa. The Europa Clipper mission, launched in 2024, is designed to perform repeated close flybys of the Moon and may finally provide enough data to address the anomaly. Its findings, as you stand here on the surface, remain in the future. The fracture to your northwest is now visibly steaming, not dramatically, just a faint, luminous fog rising from the crack's edges, where the water vapor reaching the surface immediately sublimates into the near vacuum. It catches the light from Jupiter and glows faintly orange. It's beautiful. It is also a crack in the ice over an ocean you know nothing about, and it is 700 meters from your lander and still growing. You are alone on this decision. The communications delay between Europa and Earth at the current orbital geometry is somewhere between 33 and 53 minutes each way. Your last transmission left 41 minutes ago. The response, if one has been generated and sent, hasn't arrived yet. You are experiencing something that no mission planning document fully anticipated, an active surface change within the operational radius of your lander, and you are experiencing it in real time, with no one to consult, no one to confirm your read of the situation, no one who can help you in a time frame that matters. Your instruments are telling you things you'd rather they weren't. The seismometer array you deployed on landing is registering a continuous low-frequency signal, not the sharp impulse of a single fracture event, but a sustained vibration in the 0.01 to 0.05 Hz range, well below what human hearing can detect, but present and increasing in amplitude over the last 30 minutes. In the literature, this frequency range in ice is associated with tidal resonance, the large-scale harmonic oscillation of an ice shell being rhythmically flexed. On Earth, similar signals have been recorded in Antarctic ice shelves in the hours before a calving event. You know what calving means on Earth. A section of ice shelf breaks off and falls into the ocean. The section can be the size of a city. The ocean beneath it is waiting. The ocean beneath you is waiting. You begin calculating lift-off parameters. Here is the hardest thing to sit with. Every scientist who has studied Europa seriously, every planetary geologist, every astrobiologist who has spent their career modeling what might be possible in that ocean, every single one of them would tell you that we are deeply, perhaps embarrassingly ignorant of what's really happening on this moon. We've had a handful of flybys. We've had one extended orbital mission that wasn't even designed specifically for Europa. We've analyzed the surface composition in broad terms, mapped the magnetic field at low resolution, measured the tidal deformation at the level our instruments permitted. And from all of that, we've built models. Sophisticated, carefully calibrated, peer-reviewed models. Models that tell us the ocean is probably real, probably salty, probably in contact with a rocky sea floor, probably warmed by tidal heating, probably the best candidate for extraterrestrial life in the solar system. Probably. Models, estimates. The floor beneath that ocean, the rocky mantle of Europa, where the tidal heating concentrates and the chemistry gets interesting, has never been probed by any instrument. We don't know its composition in detail. We don't know the pressure and temperature at the sea floor. We don't know whether hydrothermal systems are active, dormant, or simply absent. We don't know the salinity or the pH of the ocean. We don't know how thick the ice shell is beneath the chaos terrain. We don't know whether the plumes are occasional anomalies or regular features. We don't know what made the magnetic anomaly in the 1997 Galileo data. We don't know. 4 billion years of chemistry, in the dark, under pressure, fed by the gravitational energy of the largest planet in the solar system. And we have looked at it for 30 years with instruments that are, by the standard of what the question demands, almost comically limited. The fracture is now 1,200 meters long. It has turned. It is no longer moving away from you. You leave. The thrusters fire, and the lander lifts, and Europa drops away beneath you, shrinking from a world to a surface, to an arc to a sphere. And Jupiter fills the sky as you rise, and the surface below, that pale, cracked, restless skin over an unknown ocean, catches the sun's light and glows a faint blue-white, serene from up here, almost featureless, almost peaceful. You watch it until it becomes a disk, and then a point, and then one of many points in the dark. But here's the thing that doesn't leave you, the thing that will still be with you when you're back in the warmth of the ascent module, when you're eating your first real meal in hours, when you're writing the report that will be read by people who weren't there. It's not the fracture, and it's not the steam rising from the crack, and it's not the dosimeter numbers, or the seismometer data, or the proximity of that growing line in the ice to your landing struts. It's the realization that the ocean beneath that ice has been there for 4 billion years. It has been receiving the energy of Jupiter's gravity every single orbit, every 3.5 days, for 4 billion years. It has been circulating and mixing and processing chemistry and interacting with its sea floor in ways we can only speculate about for a length of time that makes the entirety of complex life on Earth look like a footnote. And we have never looked inside it. Not once. Not even a little bit. Whatever is down there, if anything is down there, has had 4 billion years of uninterrupted darkness and warmth and chemistry, with no one watching, no instrument, no probe, no light, nothing from the universe outside to interfere with whatever process has been running, and running, and running, since before the first animal ever moved through the oceans of Earth. And you were just on the lid. You shifted the weight of a landing craft, a few tons of metal and fuel and scientific instruments, onto the surface of that lid, and the ice beneath you moved. It moved measurably, detectably, on a timescale of minutes. Whether that was the ordinary response of a dynamically active ice shell to a new thermal contact, or whether it was something else, some feature of a system more complex than our current models account for, you cannot say with certainty. The data will be analyzed. The seismometer records will be pored over. The magnetic readings will be compared to every baseline measurement ever taken. But you were there, and you felt it. And the part of you that was shaped by hundreds of thousands of years of evolution in environments where things that move unexpectedly are dangerous keeps coming back to the same question, irrational as it is, scientifically unfounded as it may be.